So here again is a figure that we looked at just a little bit ago, kind of from left to right. It's showing you how over time, basically planetesimals kind of accretion is the process we call about making planets into one large object we call planet per track. But as you know, there are some kind of miscellaneous rocks associated and icy rocks, regular rocks and icy rocks, asteroids and comets associated with our solar system. That is definitely not a planet. So we have leftovers. Okay. And honestly though, if you look over here, I'm going to go ahead and make my pointer so I can draw. If you look over here, so this is the first scenario, second scenario, and this is kind of like what we see now. Over here, we definitely, or go to 2 if you want to, we definitely had our time where there was more chaos, is my point, in the solar system than there is now. Okay, so kind of related to that chaos, you see this idea of we see the moon is a beautiful specimen of kind of a snapshot frozen in time of being cratered. Now, the moon is not now being heavenly bombarded with rocky material. Okay, so that's kind of like a distant past sort of thing. So there was definitely a period where things were still kind of settling down. And actually related to that, being struck by miscellaneous objects, it's thought, we really think now that the Earth's water, now based upon what I said about water not being able to condense on this side of the frost line, where did we get all of our water from? So it's thought that, like you can see on the slide, that basically in the chaos there were actually chunks of maybe even planetesimals or rocky material that was beyond the frost line, kind of zipping close to the sun and then back out, close to the sun and then back out. And that's actually, we got hit a few times, okay, and built up our water supply associated with our planet. So it's all kind of works together. Kind of related to that then, the tilted axis of rotation of Uranus and our beautiful moon can also be related to go back to kind of this heavy bombardment time. During the time when there was more chaos in our solar system, what you're looking at here are actually moons of Mars, Phobos and Deimos, and I can never remember which is which. Okay, but they're not like our moon. They're actually captured moons. And they could have just kind of gotten too close to Mars and have been there ever since, when there was more miscellaneous, more chaos going on in our solar system. So our moon is not like Phobos and Deimos. It's not captured. So kind of talking you through, there's actually kind of 3 frames here. This is the first frame. Okay. This is the second frame. Okay. And this is the third frame. And each one of those are looking through those frames in order, they describe how we got to have our moon, or how our moon got to be. So basically an impactor about the size of Mars, okay, was rambling around early on in the formation of our solar system. Notice that it's going to impact the Earth. This is the Earth right here. Okay, and the Earth had already kind of formed its crust. We're going to talk about planetary differentiation. The heavy stuff had settled. The light stuff had risen. It kind of had a crispy crust. It wasn't necessarily molten. Bam! It gets hit by an object about the size of Mars. And you can see in the second scenario that basically it kind of re-liquefies, okay, from the impact. And it tosses off some of its crust. Okay, so that's kind of, this is the Earth again, and it's tossing off some of its lighter materials, okay? And then honestly, over time, this 3 here, this ring of material, and I should go counterclockwise, shouldn't I? This ring of material then accreted, we've used that term as far as planets getting larger and larger. This material in here gathered together and created our moon. Okay, so our moon's large. And actually, our moon is a part of us. The rocks we find on the moon are very similar to the Earth's crust, which makes sense in this scenario. And it also kind of the chaos we've been talking about. This is definitely feasible early on in our solar system. So Uranus, Okay, remember, anytime you see a picture of Uranus, you should probably kind of see it tilted like that. You can kind of see the ring around Uranus. All of the gaseous planets have moons too, but it is actually, this is its axis of rotation, it's spinning, and actually its axis of rotation basically lies in the plane of the ecliptic. Okay, and it's thought that instead of being perpendicular like you would think an object would be, okay, it was because it was impacted that that actually has made it lie down in the plane of the ecliptic. Okay, so that all works. So to kind of just summarize what we've been talking about as we talk about the nebular theory, kind of start up here with a solar nebula. Okay, it has rotation, it collapses, and the rotation, how do I say this? It goes faster and faster, conservation of angular momentum. Okay. Here you can actually see kind of some colors, kind of some icy material out there along with rock and metals. And then we see the rock and the metals that are going to actually kind of accrete and form the planets, the rocky inner planets and the outer Jovian planets that have their own kind of like little mini system of moons around them. And then actually here we see us today. Okay, so that's kind of a summary